This is a protein crystal. It's pretty small, at just 1/10 of a millimeter thick, but the millions and millions of protein molecules stacked inside it are even smaller. This is Oxfordshire. It's about 50 kilometers in diameter, somewhat larger in comparison, but it's where scientists from around the world come to analyze their tiny protein crystals. And that's because it's home to this.
The diamond light source, a particle accelerator that can generate beams of light 10 billion times brighter than the sun. Compared to our crystals, the diamond light source is absolutely gigantic. It's the most expensive and sophisticated scientific facility ever built in the UK. The instrument in this building can produce X-ray beams powerful enough to peer right into the atomic heart of all kinds of matter.
Diamond is used by scientists in many different fields, but nearly half the users are structural biologists doing X-ray crystallography. This is a technique that allows us to look at the structure of any biological molecule that we can crystallize. The secret of success is growing crystals, which form when molecules pack together into highly ordered structures. This ordering of the molecules means that when we fire X-rays at a crystal, it diffracts or scatters the beam into hundreds of intense rays. The resulting diffraction pattern, detected as an array of spots, is dependent on the internal structure of the crystal. And by measuring the intensities and positions of these spots, we can work back to the structure of the molecule it is made from. It's a method that has opened our eyes to life at the molecular level.
X-ray crystallography isn't a particularly new technique. In fact, it's been around for about a century. In the early days, crystallographers used simpler X-ray generators and photographic plates like this one to record their diffraction patterns. Back then, X-ray generators were much weaker, and this tended to limit the technique to larger crystals, which could usually only be grown from smaller and simpler protein molecules. Even then, it could take hours or sometimes days to record all the diffraction patterns needed to solve the crystal structure of a protein. But today, with synchrotrons as powerful as diamond, we can use much smaller crystals, down to only 5,000ths of a millimeter in size, which is often what you have to do if you're trying to study larger and more complex proteins.
Here at the core of the synchrotron is a particle accelerator ring that accelerates electrons to close to the speed of light. The ring itself is around 560 meters in circumference, and dotted around it
are undulators like this one. Powerful electromagnets within this pipe force the electrons to wiggle from side to side as they pass through. And as they wiggle, they produce an intense pulse of electromagnetic radiation in the form of X-rays. And that pulse of X-rays shoots straight into one of the lead-lined experimental hutches where visiting scientists carry out their diffraction experiments. During the experiment, the crystal, which is mounted on the end of this little pin, is cooled by ultra-cold nitrogen gas from this nozzle to help it withstand the punishing radiation. This allows us to take much longer exposures, which are needed when working with very small crystals. The X-rays from behind emerge here and are scattered by the crystal into many different angles. The diffracted rays are captured on this detector, which can record up to 25 images a second, much faster than the photographic plates that we used to use.
So what do we do with this information? How do we convert these diffraction patterns into molecular structures? Well, I can see my crystals down a microscope like this fairly easily. What I'm doing here is using lenses to make a magnified image of a tiny object. And that works because the lens can recombine or focus the light scattered from an object to make an enlarged image. Because a molecule is much smaller than the wavelength of light, I'm never going to be able to see it using an instrument like this. Instead, we use X-rays, a form of light that has a wavelength about the size of an atom. But there are no lenses to focus X-rays, so we use our mathematical understanding of how light scatters to do the work of the lens for us. And that allows us to work backwards from the diffraction pattern to a three-dimensional image of the protein in the crystal.
What we end up with are three-dimensional maps which plot the electron density of the protein molecule, and this reveals its branched, chain-like structure. The resolution of these maps is dependent on the quality of your crystal. The better they are, the more accurate your model is likely to be. Originally, crystallographers would painstakingly build these 3D models by hand, but now we rely on computers to generate them. With good quality data, these maps are stunningly detailed. You can see the lumps and bumps of every atom, every twist and turn of the protein chain. Even after you've spent your time at Diamond and solved your protein structure, you've really only taken the first step on a much longer journey towards understanding how it works. But from these sorts of investigations, we can learn how the biological molecules of your body interact with one another, or how to design drugs that will bind to them more effectively, or even to design proteins that nature never got around to inventing. Even after 100 years, these are still exciting times to be working in structural biology, thanks in no small part to facilities like Diamond.